So, chapter 4. Let's just forget about that. Put it out of our minds for now, not worry about it. Chapter 4 is not very long, really, and it kind of continues this trend of what we were doing in the last chapter. Chapter 3 and 4 really go together. We're going to continue to look at interference effects because light is a wave, except we're going to sort of expand the idea just a little bit and mix these chapters together. By the way, this stuff on the board, do you miss it a little bit? Do you miss your old friend here? We got B.dl, and this looks like some current creating magnetic fields through little semicircles and stuff. No, you don't want to talk about that anymore. Just, okay, understood. You like the new stuff. Fine, I'll stand in front of this. You don't even see it back there, okay? What's that? No? We could just jump back and do chapter 28 again. Not 28, not this class. Hold on. I don't know what chapter it was. I'm lost. I can't keep these textbooks straight. It's confusing. Let's see. So chapter 4, take a look at what's up here. Diffraction. Diffraction we could define as the bending of waves as they pass by either a barrier or some opening of some type. So last chapter we were dealing with like 2 openings. We're going to shrink that down now and just look at what happens when light passes through a single opening. Keep in mind, with all of these types of effects, we are looking at interfaces that are at least roughly, we'll say the wavelength of the waves we're looking at. So if we're dealing with light waves passing through an opening or a barrier, that interface needs to be on the order of magnitude, at least, of the wavelength of light. So we're talking nanometer-size openings. This effect also happens with other types of waves, but perhaps with bigger openings if you're dealing with something with a larger wavelength. So like sound. If I were to stand out in the hallway with the door open, let's say, and maybe you were to stand right here, and I say something out in the hallway, I don't think any of you would be surprised if you heard what I said right around this corner. Agreed? It's not like you need to be right in the path of the waves for the waves of sound to hit you and for you to hear it. As it goes through this opening, well, apparently the sound waves can bend around that opening, okay? In other words, it's kind of like what you see on that left diagram. There's an opening, waves are going through, and as they go through that opening, they bend such that they spread out in all directions. We described that last chapter as Huygens principle. When there's an interface or an opening, the wave sort of restarts as if it's coming from this new source and spreading out everywhere. Good so far? Yeah, perhaps, okay. Because this happens, it also can lead to additional interference effects. And you can see these effects in a number of different ways. I don't know that this is helpful at all. It looks like a pair of scissors, but maybe it's not. Maybe it's weird eyes and like an eyebrow that's going up. I mean, who knows? I don't know. Take your fingers, finger and thumb, put them really, 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 really close together and try to look through that tiny space. If you can get them just close enough and maybe get a source of light behind it until you get perhaps dizzy a little bit, you might at some point see like a piece of made-up flesh maybe that's like in between the two. You see that first of all? And then if you get a little bit closer, you might start to see some bands of interference, kind of like they show around that pair of scissors. Do you see it? Or are you just going a little bit insane trying to stare at your fingers? Don't look at me through there, because maybe go right at the lights, perhaps. I think it's a little better if you do that. In that particular case, if you can start to see those interference bands a little bit, your fingers are really close together. They're being forced through this little opening, and you can start to see some interference effects that we're going to explain a little bit. Some of you are freaking out now. Are you okay? No, neither of you are okay. Both of you are like, yeah, what's happening? Yes. Well, when I say pass by a barrier, so perhaps even if we didn't have just a door that was open, if we got rid of all of this, well, you could just say that sound goes past this barrier and still bends around it. So it can go around a barrier to get behind it or through an opening consisting of 2 barriers. roughly the wavelength of light. So roughly the wavelength of the wave that you're considering. Here we're talking about light waves. Yes. That's other stuff. In that particular case, sound can still go through materials just like other types of waves. Refraction, transmission, echoes. There's a number of ways that the waves can get through. Okay? Anybody else? Well, we haven't really even done anything yet. There, we got this slide. Let's just ignore this thing over here. I don't really care about that part. Okay? So as we go through this chapter, we're essentially going to look at a number of different types of openings. And I'm basically just going to give you the equations and describe the different experimental setups. Some of this stuff, it turns out, will come up in lab at some point. So you just sort of need to know it. It's a lot like the optics chapter where it was like you have all of these rules for this situation and all of these rules for this other situation and all these rules for this other situation. It's a little bit irritating. A lot of that stuff will either be on your equation sheet or you'll have your page of stuff that you can write down to try to keep track of all this. Okay? So let's start with the first one. The first one is dealing with diffraction through a single opening, so-called single slit diffraction. If you have a little opening of width W and you shine light waves on that opening, it doesn't do what you might expect if the opening is really small. If the opening is of any width at all, you might expect that I shine light waves here and pencil is not working. Try again. And you might expect that what would happen is just like, oh, light would go through the opening and you would get a bright region here and then just darkness everywhere else. That seems to be the logical case. But as that opening gets smaller and smaller and smaller and starts to get really small, sort of on the order of the wavelength of light, you end up with interference effects because the light hits the opening and then spreads out in all directions on the other side. The only way that we can explain this, and I'm sorry, you'll have to just sort of accept this theoretical idea, is what we might call Huygens principle extended. Huygen's principle extended. So we could say that the light behaves as if every point in the opening is a new source. The light behaves as if every single point inside the opening is a new source of light, and it spreads out from all of those points just like we did with the openings for the last chapter in the double slit experiment. So in other words, this diagram that we have here isn't really the best. Let's redo this just a little bit. Let me get rid of these lines. What's really happening is sort of like if I were to zoom in here, like this point acts like a little tiny opening and light spreads in all directions from that point. And then the point right next to it, I should probably switch colors, right there, acts like a new source of light, and light spreads out in all directions from that point, and so forth. Every little spot of space in between the two acts like a new source. So it's almost like I have an infinite number of new sources of light contained inside that little opening. Okay? If that is true, then we have the same sort of thing where every one of those sources is creating light, and as it goes out to a screen, all of those light rays are going to travel a different distance a little bit to get to a certain point. So really, it's like, I don't know, the double slit experiment, like to an infinite extreme. All right? We have an infinite sources of light contained inside that. I can't explain that any further other than to just say, okay, good enough, maybe, perhaps, yes. You don't want to argue too much? You want to argue? No? Okay.
So the same thinking of like the multiple little spots, like the multiple little sources.
Mm-hmm.
Say that for the double slit?
Yeah, that's technically happening back there as well. We'll address it about halfway through today's lecture. Okay? Notice over on the right, They are dealing with the math of this situation by pretending that there is a source of light right near the top part of the opening and then looking at one leaving right in the middle. Keep in mind, this is just two of an infinite number of beams that are sort of leaving and traveling parallel out to some point on the screen, all right? Once again, they describe what the path difference is here, which is this little line, which is this case W over 2 sine theta. And I'm not going to do all the work we did last time. Just keep in mind, this is representing a difference in the path length out to the screen. And you get a really similar looking equation. So we could say that W sine theta is equal to m lambda, where m is equal to plus or minus 1, plus or minus 2, and so forth. However, this is for the centers of totally destructive interference. The centers of totally destructive interference. In other words, over on this diagram, this location would describe m equals 1. This location would describe m equals negative 1. And this one would be m equals 2. And this one would be m equals negative 2, and so forth. Okay? Yes? If there is some region where it's dark, this is the exact location of the middle of the dark region, okay, where it's perfectly destructive. You don't really have to do a whole lot of work for the regions of constructive interference. They're just halfway in between the destructive places. So let's see, constructive is halfway between, we'll say, the above. So in other words, if I just figure out where m equals 2 and m equals 1, where those regions of darkness are, I can go exactly halfway in between, and that's where the region of perfectly constructive interference is going to occur. So I think this is actually a little bit easier, okay? Now, I need to point out, even though we're not going to do the math of this at all, there's a whole section on all of this. We're just skipping over it completely. Notice in this diagram, they sort of do this like, hello, work, there we go. They draw all of these regions of brightness as if they're exactly the same. That's not true. They're not all equally bright. This middle one is going to be very bright, and then it decreases in brightness the farther I go out until they fade away, okay? So there must be a better way to draw this. Let's just write it here. This one is much brighter than the other bright bands. And then we'll say in both directions, decreasing brightness. Okay? Who's got questions? Got the basic idea? It's kind of more of the same. We're going to sort of build toward things that are a little more useful as we go through today's lecture. That might seem like, great, fine, you passed light through a hole. Congratulations, good work. It's, again, one of these experiments that it proves that light is a wave. So take that equation we just had, W sine theta equals m lambda, and answer this question. Yes? Yeah, but better thought of maybe more as an indicator. It's telling you which particular dark region you're talking about, measured away from the central one. So it's like describing the third one, or the fifth one, or the first one. Mm-hmm. And they're meeting in such a way that they destructively interfere. Yes. Anybody have the answer here? Thoughts? Maybe? Vote with your fingers? 1, 2, 3, 4. Go. Now. Please. I beg you. I see ones. I don't think it's one. Oh. Now I see twos. Oh, I see what's happening here. I don't think it's 2. Now you're all like, 3. Like, no, it doesn't work that way. W sine theta equals m lambda. So let's see. If I want to make the central bright spot narrower, that would be the same as trying to make this go down. If I want to make it smaller, it's like the angle out to these different points needs to decrease. The way I do that is by making this a little wider. Not too wide. If you make it too wide, like the whole thing kind of falls apart. But by making it wider, we can sort of shrink the pattern. So widen the central slit. Okay? Use the same thought process to work through this idea. Yeah?
How do you know you changed the theta for the first?
Theta is, if I just use this diagram, is describing how far it is angular from the middle out to one of the bands. So if I'd like that to be smaller, I need sine theta to decrease as well. W sine theta equals m lambda. This time we're trying to keep things the same. Even though we've changed the wavelength of light, we're trying to keep the exact same pattern. So what do you have to do? Who says 1? 2? Now, which one is it? Vote. 4? You like 4? 4? I like 4. 4 sounds good. So if I make this 2 lambda, I need to do something to the other side to keep it exactly the same. So I need to make this a 2 as well so that we have exactly the same relationship. They're using D here to represent the width. That's fine. We just need to multiply the other side by 2 as well to get the same pattern. Okay? And then finally, we haven't really talked about this, but I'm thinking that maybe you can come up with the answer. Use everything we've talked about interference and what has to happen to give you different interference effects and see if you can come up with something. That time of year, iced drinks have come back. I see iced coffee, maybe an iced tea over there. I just had an iced coffee. I feel good. I want another one now. I'm okay. Don't laugh at me. I'm only a little bit addicted to such things. Does your drink feel in danger? It's a little close. It's not even, you don't care? I can have it? You don't like it? Oh, you like it, but I can have it. You're a little scared right now, aren't you? It's like I feel like too much of an addict for coffee that maybe... What is it exactly? What would you get? Is it a latte? Yeah? Yeah. As long as it's not banana flavored, I'm pretty good. I can't think of anything else you might put in there that I'd be like, Any thoughts on this? You think it's 1? Anybody else say 1? 2? I see some 2s. 3? 4? What if I told you it was 2? Here's the way we're going to describe it. I'm going to say that there are 2 representative beams. So maybe imagine one leaving the top and one leaving the bottom and trying to make its way to the center of the screen. Okay, so let's say that there's a light ray here that goes to the center and one that goes here and to the center. What can you say about the distances those rays have traveled? It's the same, right? Same distance. If they travel the same distance, what about their phase? Are they in phase, out of phase? They are in phase. They've traveled the same distance, which means what's going to happen in the middle? They're going to constructively interfere and give me a bright spot. Okay? So we could say that they arrive at the middle in phase. You might guess we would get a different answer if maybe I had asked about some random point like right there. Right? In that case, those sources of light have traveled a different distance, and I would need to do a little more calculation to try to figure out whether they're in phase, out of phase. I'd need to know the wavelength, perhaps, and we'd have to do a little bit more work. Okay? You might also guess that, like in this particular situation, you might get some like rings kind of like this that are like interference bands. We're not going to do too much with that, but just to give you the idea. Yeah? How often do you see a tiny little thing blocking the light, though? So if I had a disc there that, notice this is a laser beam that might not be very wide. If I blocked it with a disc that's really small, you would see interference effects. But just like, I don't know, if I'm standing in the way of a beam of light, you're not going to see something like that. You need to get down on the order of wavelength of light to see the effect. Even if it's a big beam of light, you haven't changed the wavelength of light itself. So it's all about what the wave is doing. Change the different type of wave. Talk about sound waves. You could perhaps have regions where maybe you couldn't hear the sound because of a barrier because it traveled a different distance to a place. You should, yeah. Right in the middle, you would hear it because that would correspond to a bright spot. Okay? All right, let's talk about the next case. And this is what you brought up a few minutes ago. Double slit diffraction. Each one of those slits actually acts like what we just talked about, where every little point inside the slit is causing sort of single slit diffraction as well. So we didn't talk about it in the last chapter. We just sort of pretended that with the two slits, there's a region of brightness in the middle, and then it's dark, bright, dark, bright, dark, bright. And we just pretended that eventually it went away, but we didn't talk about the intensity of those bands. It turns out that they are really bright in the middle and decrease in brightness as you go out as well, because both interference and diffraction are happening together. How about that? That's kind of fun. I didn't even have to write anything, okay? So the interference effects, this stuff here, showing places where you have a bright constructive interference, that's what we talked about in the last chapter. So we'll call this two-slit experiment. Simultaneously, what we just talked about earlier in this chapter is happening, and it could be represented by this blue curve. So you can see you have a wide, very bright central region. And then notice as I go farther out, there's like a complete decrease in the intensity. So this would be one of my dark regions. And then the intensity goes back up a little bit, so that would be bright. Notice how much darker that is compared to the central peak. So it's a pretty pronounced effect. That central region is really bright, and those little bright bands that surround it are much, much darker, but still there. How do you combine these two? It turns out that it's not additive, but you multiply to get the overall effect. It's a multiplicative effect. So you can see that here they're just using sort of relative intensity, so everything is sort of normalized to 1. But if I have places where one of them is 0, take a look and see what happens. So where is our total sum effect? Let's go here. Notice at this location, the interference pattern is 0. So when I multiply it by the diffraction pattern, which is a little bit non-zero, the total is 0 at that point. Okay? If I go over to this location, notice the interference pattern should exist, but the diffraction pattern, the red line is 0 at that point. When I multiply them, the blue line goes to 0 there. Okay? So you're multiplying the two patterns by each other, and you end up with something sort of strange overall that is represented by that red line. Okay? The two effects together we are not going to deal with mathematically because calculating those intensities is a bit of a mess. I'm not even going to put anything else on this slide. You just need to know that this is happening. End of story. Okay? Don't you love the detail with which we're covering things at this point? Yeah. Yeah, it can cause problems. It might be frustrating in some cases, and in other cases you're just like, yay, sounds like a multiple choice question. And then you're going to get all the multiple choice questions right, and that's going to be fantastic. Agreed? Yes. Mm-hmm. Uh-huh. Yeah. M is the dark spots. Yeah. Just a remnant of the calculation. You could set up an equation for diffraction to find the bright spots as well, but that's just not the standard way it's done. Anybody else? Next slide. Now we're going to expand on that circular opening just a little bit. So ignore the thing at the top, the idea of resolution. We're going to talk about that in just a second after I describe more about light passing through a circular opening or a circular aperture, which is usually the word that's used. Just think of an aperture as a tiny little hole, okay? When we're talking an opening that we're letting light pass through that's tiny, we're literally talking so small you might not be able to see it, which makes things a little bit tough. I have both taught and done lab experiments before where it's like you try to get students to reproduce this pattern. Sadly, we did this at one school where it's like, make your own circular aperture. So it was like, we gave them a piece of like an index card and a really sharp needle and said, make a hole in it that you can't see. Clearly they found this frustrating, right? So it's like, they would be like, well, I think I made a hole, and then they had to take a marker or something and like put a circle around where they think they made the hole, and then try to shine a laser at the hole that they can't see. This worked fantastically, as you can imagine, all right? If you want this to work really well, you need to have some manufacturing company that has great precision, put a hole in some sort of object that's really, really tiny, and then say like, hey, the hole is here, shine your laser at this location. Because again, we're talking about openings and interfaces that are really, 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 really small, okay? It turns out that experiment with the index card and stuff, it can work. You just have to be a little patient and like really carefully make a tiny little hole that really doesn't have any rough edges and stuff around it. And I don't know, you can spend the 2-hour lab period just trying to like get the hole to create the pattern. But I don't know, it's a little hands-on, it works. When the students got it, they were like, yay, I made a circular aperture. And I'm sure they'll brag about that for the rest of their lives. Hang it on their fridge, be like, there's a hole in this piece of paper. Can you see it? No. So, what does this look like overall? Let me add a slide here because I really need to draw this out in some more detail. Let's say that from the left we have some light. Whee! There's light. Why did I make it go up at the end? I don't know. Whee! Light. Whee! Light. And then it encounters some sort of screen, and in the middle there is a tiny little hole. I will actually magnify it a little bit so we can see it and understand what's happening. After it goes through this hole, over here somewhere we have another screen. And on this screen you see something that looks like this. And where I'm actually drawing, consider that to be the bright regions because I don't know how to draw darkness. That's just a little odd. So we'll say, let's just call this a bullseye pattern with a bright central spot. That looks like spat. That's not good. We don't want spat. Spot. And bright rings. And for our equations, let me set up a few different things. There's going to be a certain distance between these two. We're just going to call this L. And this little hole is going to have a diameter D. Okay? Good so far? Everybody's happy? All right. Let me go back to the previous slide because I want to draw on the actual pattern that's there. You got that bullseye pattern, bright central spot with bright rings around it. It literally looks like something like you see here on the left, and we have some equations that describe different parts of this. So let's see here. No. This thing in the middle, this bright ring here in the middle has a name. It is known as the Airy disk, and it has a radius, which we'll call R1. And you can find that radius to be equal to 1.22 times lambda n times L over D. Remember, lambda n is the wavelength of light inside your experiment, so between the circular aperture and the screen. And don't forget, it's equal to lambda over n, the index of refraction in that material. So this is the wavelength of light between aperture and screen. And there is a second equation, R2, which is the distance from the middle out to the middle of this first bright band, R2, D2. And it's equal to 2.23 lambda NL over D. Again, D is the diameter of the little tiny hole. Let me see if there are other equations I need to give you before I tell you what we're going to do with this. And of course, there are equations for the ones farther out. We're not going to worry about that so much, okay? Here's the thing. Notice that if I'm looking at a source of light, that if that light goes through a small hole, and maybe the light is some distance away, it turns out if the light is some distance away, the hole can be larger and we still get these interference effects, okay? That the image of that light on the other side of the hole isn't like a perfect bright spot. So imagine if I'm looking at a star some distance away, and it's like, ooh, that should be like just a little pinprick of light. It turns out that like back on my retina, perhaps you see something that's a little more like this, right? Where there's a fuzzing of the image because of these interference effects kind of spreading it out in space. So the problem is if I'm looking at two sources of light, it might be possible for something like this where the interference patterns of those two images overlap with each other, and maybe I can't even tell that I'm looking at two different objects. There's some limit to my ability to distinguish between closely separated objects because of this interference effect when I look at light through a small opening. By the way, on this next slide, we could just do something like this. I don't know why it's shaped like that, but, you know. It's kind of an eye, right? If you think about it, there's a small hole, the pupil in your eye, and then there's a screen in the back. That's the retina. Yes, this is a problem, okay? Basically, small hole and screen is your eyeball. So let's just eyeball. By the way, just saying eye is less fun than saying eyeball, don't you think? So let's just call it eyeball. Why not? So it turns out that we have a limit on our ability to distinguish between two objects because if those two central bands get close enough that they're actually touching, well, then all of a sudden I just see one bright central ring, and I'm no longer seeing two objects. You have something that looks like this at the top. So we're going to try to find what is the condition where they are just barely separated, like in the picture at the bottom, where it's like the first dark band overlaps with the first dark band of the other one, and then I can clearly see that I'm looking at two different sources of light. Got the idea? Okay, this one has a fancy name. It is known as the Rayleigh criterion. I like it. Sounds very Star Trek, don't you think? Just a little bit. Like, we can't go any faster. The Rayleigh criterion will be forfeited or something. I don't know what's happening here. It just sounds extra fancy. I think Rayleigh just wanted, he's like, don't call it the Rayleigh condition or the Rayleigh What else is just boring? Rule, the Rayleigh rule. You know, he's like, call it the criterion, because that just sounds fantastic. This is the minimum angular separation necessary to see two objects, we'll say separately. The minimum angular separation necessary to see two objects separately. So theta min is equal to 1.22 lambda over d. And it turns out we can use another one of those small angle approximations, which I won't describe in detail. I just want to give you the equation because it's easier to use. Small angle approximations gives us this equation. X over d is approximately equal to 1.22 lambda n over little d. And now I need to look at my notes and remember what some of these symbols mean. Terrible, right? Okay, something like this. So let's say that this is the little aperture, and out here somewhere are two objects. There's one, there's another one. X is the distance out to those objects. No, it's not. Big D is the distance out to those objects. That's a terrible D. And the separation between them is X. So you might imagine that theta min from above is just how far apart they are by angle. So if I were to draw this line and that line, that is theta min. How far apart by angle do they have to be? That is a terrible diagram, isn't it? Feel free to laugh at it all you want. Maybe you're not, but it seems terrible. But could we zoom in a little? There we go. Actually, let's get rid of a couple of these x's. We'll make this like a source of light, separated by distance x, a distance big D away. Theta min is the angle between those two from my vantage point. So this is our aperture. We're going to do an example problem with this in just a minute, assuming there's time, and you'll kind of see how this works. It might have to be Friday, though. Yeah. Is this only for eyeballs? No. Could be anything that restricts the light such that it has to go through a small hole. Yes. It's the thing the light's going through. Yeah, so these are the sources of light. So if it helps, just think about trying to look at two stars in the sky that are really, really close together. Or maybe you are driving at night and some car is approaching you with headlights on. That's two sources of light, right, separated by some distance. When it's really far away, do you really see two different headlights? No. You see one light, and then as you get closer, you're able to resolve them separately, okay? That's essentially what's going on here. We will save the example problem right to the end of this chapter, though. We'll see if we get there, all right? Any questions about that before I add one more condition, and this is the one that you're actually going to see in the last lab, I think, of the semester, so I want to make sure to include it, even though this particular section isn't included on the syllabus. But we should talk about it because it's important for lab, all right? And that is the diffraction grating. The diffraction grating basically involves many slits, okay? So think of it something like this. It's a little apparatus, maybe it's a card that looks like this, and if you were able to look at it really, really closely, you would find that there are a bunch of like vertical lines that are acting as holes for the light. If you've seen a diffraction grating, which perhaps you'll see in lab, often the ones that we use in lab are just like a little card that's like this, that has like a little plastic window that you can, it's transparent, you can see through it, But the only reason it's transparent is because there are so many little lines that are carved in it, and they're so close together that it might as well be something that's see-through. It's just not perfect. Like, you look through it and you're like, it's kind of hazy, kind of rainbowy, but that's because of all these little lines really close together. Yes? A polarizer be a diffraction grating. I could imagine that it could be used as one because of the orientation of the molecules, but I haven't heard of that case specifically. It would make sense, though, especially considering what we're going to talk about on the next slide. Okay? So think of this as just sort of the extreme case, all right? And you might be thinking, why bother with this at all? There are two specific cases on the next slide that tell us where we can use something like this. And once again, let me just sort of draw out what the experiment looks like. We'll have a source of light from this side. It tries to get through all of the little holes, which act like a bunch of different sources of light, and that gives us an interference pattern over on some screen. It turns out this time the interference pattern looks something like this. You end up with a series of bright dots that sort of fade out as you go farther to the side. We're going to describe this again as the distance L. And I need to add a few different things here. We're going to let little d equal the separation between slits. Often lines are used interchangeably here because these slits are often fashioned as long lines that go all the way across the diffraction grating. We're going to let little n be the number of lines or slits per width, which means I can start to describe a couple of equations that relate these two things together. So d is going to be equal to 1 over n, which is equal to the width of the diffraction grating divided by the total number of lines. And if you just look at that equation, I think it should make some sense. Okay, if you start with the right side, I take how wide the total diffraction grating is and divide by how many slits I put in there. That should give me d, how much separation there is between each one. And if you take n, which is the lines per width, and flip it upside down, it makes sense. That would be the number of lines or slits per width. That would be width divided by the total number, which is exactly the same thing that we have over on the right. Okay? Yes? Yes. Okay? And once again, we have a really similar looking equation. D sine theta is equal to m lambda. This time m is equal to 0, plus or minus 1, plus or minus 2, and so forth. This is for constructive interference. We can say that sine theta is approximately equal to y over L, which means I can simplify this to be d y over L is approximately equal to m lambda. And that is the one you're most often going to use. So if I look back at this diagram at the top, the central one is for m equals 0. That one right next to it would be m equals 1. One on the other side would be m equals negative 1, and so forth. Okay? Yes? It's getting less bright because of the diffraction effects on top of the interference effects once again. So it's kind of a combination of last chapter and this chapter. You don't have to worry about the brightness in this class. We are skipping the sections about the intensity of the light. But just so you recognize what you're seeing, if you see this pattern in the lab or somewhere in nature. Okay? We've got 5 minutes left. It's not going to be enough time to do the example, but it is going to be enough time for me to describe why in the world you might want to use a diffraction grating. So first of all, maybe you've heard of X-ray diffraction. X-ray diffraction? Anybody done X-ray diffraction? Your hand went down fast. Why so fast? Like, no, I would never do X-ray diffraction. That's terrible. X-ray diffraction allows us to do something like determine the structure of, I'm going to say, for the most part, solids. So if it's a crystalline solid, you can find out like the lattice structure of all the elements together. X-ray diffraction was used to determine the helical structure of DNA. Just to find the structure of basically anything, you can shine X-rays through it and use the diffraction effects to find what that structure looks like. As you can imagine, it's much, much more complicated than something like this. What's happening, though, is that the different planes of atoms act, or we'll say the spacing between, rather, act as the slits that you're passing the light through. So a lot of computation is involved. If it's something that's relatively simple, like copper has a cubic structure, so it's basically just rows of atoms that are two-dimensional planes, and then right underneath that is just rows and columns of atoms that are in two-dimensional planes. You could sort of imagine how then it's like, ooh, I've got a bunch of atoms here, and then there's a bunch of atoms here, and there's a bunch of atoms here, and then I shine light this way, right? It has to get through these openings in between. Well, then if I do that and work through this experiment and go back to the previous slide, and I know the wavelength of my light, and I make these other measurements like y over L, I can find the spacing in between those planes of atoms by sort of working the experiment backwards. So instead of creating the diffraction grating, nature is my diffraction grating, and we can find that spacing. If it's a more complicated structure, you could take the object and put it in different orientations. And as I look at something that's complicated from different ways, like sometimes the symmetry sets up where it's like, ooh, from this orientation, I see like planes of atoms that are like this. And then I rotate a little more, and then I see planes of atoms in some other orientation. If you do that enough, eventually finding all of these different spacings allows you to computationally determine what that complicated structure looks like. It's sort of easy to visualize if they're planes like in copper. Imagining trying to do those calculations with something like DNA sort of breaks my mind a little bit, and I don't even want to think about it too long. But that's the basic idea, using the material itself in nature as your diffraction grating to find the spacing between the atoms, okay? Another thing you can do is the grating spectroscope. And this is where I have a light source. If it helps, think of this as maybe like a star out somewhere, maybe a distant star or planet. Let the light come in, and then it will act to spread out the light into its constituent colors or constituent wavelengths of light. So if it's just one, the grating is going to bend the light in one particular direction. And this can be used to find the wavelength of light from some unknown source. Knowing the wavelength of light that something is putting off allows you to know something about what it's made of, like what is the thing that's putting off the light, because of, I don't even want to get into all that, because of reasons that you've probably heard in chemistry class, like emission spectra, electrons falling between different energy levels, et cetera, et cetera, et cetera. We're going to talk about that a little bit in the upcoming chapters a little bit, but hopefully in some other class you've heard the basics of that at least, okay? So, diffraction gratings in two different cases where we can find some interesting things about nature, both up close and far off. And that's all I want to say today. It's exactly 4 o'clock. Goodbye. We'll do the example and start whatever the next chapter is on Friday. I don't know. That's all there was to it. All right, so let's do this last slide of chapter whatever this is, 4 of volume 3, and then we're going to jump over to chapter 6. Hopefully you saw the slides that were posted this morning. It's a bit of a last second, and it's going to be fun because it's a brand new set of slides for me. It's a new lecture. You guys get to be tested on, so it might be a little rough, a little shaky. Should be fun either way, so just forgive me if things are a little bad when we get into this next set of slides. But let's start with this thing, which is way too many words, all right? Let me see if I can narrow it down a little bit. We are doing an experiment using a particular beam of light, and the wavelength is given here. It says that's from a monochromatic source, so all of it is at 570 nanometers. It's not mixed with other wavelengths of light. We are going to, it says, shine it onto some sort of aperture. And as you see below, they describe two different apertures that we're going to let the light shine through. So think of this as like setting up the experiment where I have a screen and then something to hold the light to shine through in some place. And we're going to keep the experiment fixed. But I'm going to start, it says, by using a diffraction grating as the aperture. So we're going to put that in this place and see the pattern on the screen and take some measurements. And then we're going to replace it with a circular aperture. It says a metal plate that has a hole of given diameter drilled in the middle, okay? So the experimental setup is all the same. The only thing that we're changing out is a diffraction grating for a circular aperture, okay? This is a disgustingly wide open experiment. It just says determine as much as you can about this experimental setup. Don't you wish the exams were that way? I just state some stuff. Tell me what you know about this type of problem. I don't think anybody wants to grade that, so you don't have to worry about it. I'm going to just walk you through a few different equations and setups and just show you some things we're going to calculate. It's not going to be that extensive. And then at the bottom it says, in addition, do some other stuff. We'll read that and get to that in a second, okay? So let's go over a slide where I have some blank space, and let me write a couple of notes down. First of all, the lambda, the wavelength of the light, is 570 nanometers. So that's 570 times 10 to the minus 9 meters. And just because of the way this problem ends up working out, I'm going to start with the circular aperture. The problem really should be stated in the opposite order. I can just tell you this is the best place to begin. The circular aperture. They said that the diameter of the circular aperture, which I'm going to write as D sub A so we don't get things confused, diameter of the aperture is 71 micrometers, 10 to the minus 6. What else did they tell me about this particular experiment? Somebody slide back. Give me another number. Or don't. That's fine, too. That's good, isn't it? Yeah, I see you're just sipping. What'd you order? There's soy milk in it. Coffee. It's a mocha. What do you have? Huh? You're not going to tell me? Okay, it's fine. It could be too tempting. Oh, you're hiding one over here. I see what's happening. It's all down on the seat. And she's just smiling like, don't look. One of these days, I'm going to make you all jealous. I'm going to come in with just like a vat of iced coffee, like this big, and then just the whole time, I'm just going to keep scooping it out, and it's going to be fantastic. And at the end of 50 minutes, you're going to have to like tie me down or something to carry me out of here because I'll be so hopped up, it'll be sad. Can someone tell me another piece of information about the circular aperture and that part of the experiment from this paragraph? The bright spot diameter, the central bright spot diameter. What did we call that on Wednesday? The Airy disk. So this is the diameter of the Airy disk. Diameter of the Airy disk. They say that's 17 millimeters. The thing is, the equation we have is for the radius of the Airy disk, and we called that R1. So clearly that's going to be 8.5 millimeters. And we have an equation for R1 that looks like this. It is 1.22 lambda L over the diameter of the aperture. What? No? Don't remember? Just an equation that was given. We didn't do any derivations or anything. And there's only one unknown that's in there, which is L. L is the distance from the circular aperture over to the screen. So if I find L here, then I'm able to use that back with the diffraction grating because that distance is not going to change. So let's see. Let's solve this for L. So we're going to have R1 times D sub A over 1.22 lambda. So that's, let me write it as 0.0085 meters. The diameter is 71 times 10 to the minus 6 meters over 1.22 times 570 times 10 to the minus 9. Ugh. And hopefully we get an L that is somewhat reasonable. I've got 0.87 meters. That sounds like a nice distance that would fit like on a lab tabletop, right? I didn't get something like 400 meters. Like that's too big of an experiment. And we didn't get something like 6 nanometers. We can't really do that either, all right? So a little less than a meter sounds like a pretty reasonable distance for our whole experimental setup. Good so far? I don't think there's anything terribly hard there. If we wanted to, we could calculate R2 since it just said to find whatever we can. What is the equation for R2? It is 2.23 lambda L over dA. Now that we have L, we've got everything there that we need. So that's going to come out to be 0.0156 meters or approximately 16 millimeters. Yay, we found a couple of things. We should just stop there, right, since it didn't tell us what to find. That's enough. No, I don't want to stop there. Instead, we're going to switch over to the diffraction grating now. So we're replacing the circular aperture at the same distance away from the screen with a diffraction grating. And let's see, what did they tell us about the diffraction grating? It says there are 120 grooves per centimeter. I like that they're called grooves this time. Just sounds like the diffraction grating is dancing or something. I don't know what's happening. And there has to be 120 little dances every centimeter. That's a lot of dancing. I'm not going to do anything else. 120 grooves or lines or slits per centimeter. So let's write that down. 120 lines per centimeter. What symbol did we give to that? Look back at your notes. This is basically a line density, if you want to think about it that way. None of you wrote anything down, did you? I'm going to rewrite this in terms of meters, so that's 12,000 lines or grooves per meter. Nope. D equals W over N. That's some stuff, yeah. It's hiding in there somewhere. What specific variable is this, though? It's N, little n. This is the line density. We can get from the line density over to the spacing between the lines by just taking the reciprocal. So let's see, we could say that D, I'm going to call this D sub G for grading, just because we have another D now, is equal to 1 over N, so that's 1 over 12,000, which is going to give me a spacing of 8.3 times 10 to the minus 5, I think, meters. Yay, we found something about the diffraction grating itself, how much separation there is between each line, as well as determine that we had the density of the lines on the diffraction grating. Once we have that, we can use the equation for the interference pattern of a diffraction grating. That's d sine theta is equal to m lambda. And I'm going to use the small angle approximation for this, so we're going to say dg times y over L is approximately equal to m lambda. And at this point, we've got, well, an infinite number of possibilities, right? Because m is just a series of integers. I'm just going to say, find something about the first case, all right? So we're going to go ahead and just let m equal 1. And then solve. Oh, how's that solve? Look at this. What is this word? Fourier, I think it is. What happened there? Solve for y sub 1, which will be the distance from the middle to the first bright spot. We could find y2 and y3 and y4 and y50 and all of them if we really wanted to, but alas, I feel like disobeying the thing that said determine as much as you can. We don't have that kind of time, okay? But you'll be able to get the idea. So let's rearrange this. Let's see. We've got y is going to be m. Well, not m. That's 1 now. 1 lambda L over dg. And we have all of those. So this is 570 times 10 to the minus 9. L is 0.87. And dg is 8.3 times 10 to the minus 5. And for that, I end up with 0.00595 meters, which is about 6 millimeters. And that solves as much as we want to for the diffraction grating. Yes? Which one? M? It's just 1. Yeah. Unless we want to solve for y2 or y3, then we'd let it be those instead. It's the distance from the center of the pattern out to that particular bright spot. Any other questions? Yes. Take a look at the units. DG is how much spacing there is in between. So if I have lines per meter and I take the reciprocal, I'm going to get the number of meters that are assigned to each line. So that's essentially telling me how far apart they are, assuming they're basically negligibly wide. They're really, really small themselves. Anyone else? I'm getting closer to all these iced coffees right here, because all 3 of them are right here on the front row. I can reach that one now. Hide it as much as you want to. I don't see any others out there. Why are they all right down front taunting me? That looks like a bottle of milk or something back there. Can't tell. Or just a water bottle that's white. Yeah, it's you. Yeah, no, there's nobody behind you. Is it milk? It's a water bottle that just looks like a milk bottle because it's white, and I'm just imagining it's clear and has milk inside. Ugh, milk. Milk's fine, but I don't want to, drink a bottle of milk. Does anybody just drink milk just because you just, really? You'll just have, 20 ounces of milk. Okay. To each their own. It's fine. What's that? Multiply by 11. Oh, sorry. This is a 1. That is M. M is 1. My apologies. Thank you. Good question. Why don't I write meter? Might be a better question. Okay, let's do this last little part. Let me go back to the previous slide, unless someone's still writing. You all look okay. And it says, in addition, determine approximately how far away a meter stick with a bright light bulb attached to each of its ends would have to be so you could barely tell that it's 2 lights and not just 1 if you're looking through the small hole. Where is this happening? All right, so imagine somewhere over there's a meter stick, and it has 2 light bulbs, 1 on each end. How far apart are the light bulbs? Should be a meter, right? I used to teach this exact problem, and for whatever reason, it's people just sort of overlooked the fact that it was a meter stick. How far apart are they? I don't know. So they're a meter apart, okay? And we are going to look through the circular aperture, the little 71 micrometer hole, and determine how, let's see, what did it say? How far away it could be so that you can tell that it's 2 lights and they're not just blending into 1, okay? Remember that fancy phrase, the Rayleigh criterion. We're going to use that to determine this particular distance. So let's see. Let's write down the Rayleigh criterion, which tells us something about resolution. So let's go up here. We said that x over d is approximately equal to 1.22 lambda over d. And we're going to solve for d. Well, don't think too hard about that. So d is approximately equal to x little d over 1.22 times lambda. And then we'll just plug in all of those numbers. X is the separation between the 2 lights, so we've already determined that is 1. D is d sub a, the diameter of the little aperture, so that's going to be 71 times 10 to the minus 6. And then we have 1.22 times lambda, and this time be a little bit careful. I think they're just trying to confuse you here. It just says light bulbs. This is a different source of light than what we had at the start, which was a monochromatic light source. The best we can do is just assume these are just white light bulbs and sort of go to the middle of the visible spectrum. So I'm just going to estimate 550. Is that okay with everybody? 550 nanometers is roughly sort of an average for white light. So we're going to say that's 550 times, that's 555 though. Try that again. 550 times 10 to the minus 9 for white light. And I actually don't have this number. Somebody help. I bet sometimes you wonder if I'm lying when I do this. Like, I just want you to get your calculators out. I actually don't have the number. I need help. There are no lies right now. Although I did just pass another coffee. There it is. Hid that well. Yeah, you thought I wouldn't come over here. Nothing up this way? No. The sooner you calculate, the sooner this problem is over, and we can start the next chapter, which is where I get to embarrass myself since I haven't taught this particular lecture before. So, 5.8. That sounds about right. 105.8 meters. Yeah? You don't know? I'm pretty sure that's it. That seems like a reasonable number for this particular case. So in other words, if this meter stick with the two light bulbs is farther away than that, it's just going to blend together and you're just going to see one light instead of being able to distinguish that it's two. This is the barrier, the cutoff between being able to distinguish between two or just seeing one. Your question. Little d is the hole that we're looking through, which is the circular aperture. So it's d sub a in this particular case. Good question. Anybody else? No?